Welcome to our session on water. Water conservation will explore the importance of water, factors affecting its quality, and strategies to optimize its usage across various sectors. Together, let's learn how to make sustainable water management a reality. Water. Water is fundamental for all life. It makes up about 60% of the human body, highlighting its critical role. Beyond individual needs, conserving water has a broader environmental impact. It reduces energy use and helps decrease pollution, which benefits our entire ecosystem. Why it's important to conserve water. Water conservation is not only about preserving resources, it also safeguards against rising costs and prevents conflicts. By conserving water, we prepare for future droughts, protect natural habitats, ensure the availability of water for recreational uses, and support the sustainability of communities. Importance of water versus water availability. The image shows the importance of water and how it relates to water availability. Importance of water highlights the vital role fresh water plays in supporting human life and ecosystems. It covers drinking, sanitation, agriculture, industry, and the creation and sustenance of ecosystems. Water availability focuses on the concept of how much water can be used for human purposes without causing significant harm to the environment or other water users. It emphasizes the need for sustainable water management. The image demonstrates the interconnectedness of water, human needs, and the environment. It highlights the challenge of ensuring that we have enough water to meet our needs while protecting ecosystems and ensuring the availability of water for future generations. Factors that affects water quality. This list appears to be a list of factors that can impact water quality. Here's a breakdown of each item. Sedimentation, the settling of solid particles, like soil, sand, or silt, in water, which can reduce light penetration, harm aquatic life, and clog waterways. Runoff, water flowing over the land's surface, carrying pollutants like fertilizers, pesticides, and animal waste into waterways. Erosion, the wearing away of soil and rock, often due to water flow, which can lead to sedimentation and nutrient pollution. Dissolved oxygen, the amount of oxygen available in water, essential for aquatic life. pH, a measure of water acidity or alkalinity, which can affect the survival of organisms. Temperature, water temperature impacts the metabolism and survival of aquatic species. Pesticides, chemicals used to control pests, which can be toxic to aquatic organisms. Detergents, cleaning products that can contain harmful chemicals and contribute to water pollution. Litter/garbage, trash that ends up in waterways, posing a risk to animals and degrading water quality. Oil/grease, oil and grease from various sources can create slicks, suffocate aquatic life, and make water unusable. Overall, this list highlights a range of issues that contribute to water pollution and threaten the health of aquatic ecosystems. Water circulation cycle. This image depicts the water cycle. It shows how water moves through the environment in a continuous cycle. Evaporation, water from bodies of water, soil, and even plants evaporates into the atmosphere as water vapor. Transpiration, plants release water vapor into the atmosphere through their leaves. Condensation, as water vapor rises in the atmosphere, it cools and condenses into tiny water droplets, forming clouds. Precipitation, when the water droplets in clouds become too heavy, they fall to earth as rain, snow, sleet, or hail. Surface runoff, rainwater flows over the land's surface, collecting in rivers, lakes, and oceans. Snowmelt runoff, when snow melts, the water flows downhill, contributing to surface runoff. Infiltration, some rainwater soaks into the ground and becomes groundwater. Groundwater flow, groundwater moves slowly through the ground and eventually may seep out into surface waters or evaporate. Annual water consumption for hotels. The table shows the percentage of total water consumption that each area accounts for in each climate type. For example, in a temperate climate, 34% of the water is used in guest rooms, while in a tropical climate, 34% of the water is used in guest rooms. This information could be useful for hoteliers to understand how water consumption varies by climate and to identify opportunities to reduce water use in different areas. The breakdown allows hotel management to tailor their water conservation strategies based on specific areas that consume the most water in each climate type. For instance, if guest rooms are a significant portion of water usage in both temperate and tropical climates, efforts could be focused on implementing water-saving fixtures or encouraging guests to reuse towels. Similarly, if the F&B area shows high consumption, optimizing kitchen operations or reducing water waste in food preparation could be beneficial. Overall, this analysis aids in making informed decisions to enhance sustainability and reduce operational costs. Water benchmark for luxury hotels. The table shows the water consumption benchmarks for luxury fully serviced hotels in different climate zones. The benchmarks are categorized as excellent, satisfactory, and high, with lower water consumption considered better. For example, a luxury hotel in a temperate climate zone with water consumption below 0.45 meter cube per overnight guest is considered excellent, while one with consumption below 0.7 meter cube per overnight guest is considered high. The benchmarks indicate that hotels in warmer climate zones generally have higher acceptable water consumption levels due to increased demand for water for cooling and landscaping. The categorization helps hotel management assess their water usage against industry standards, encouraging them to implement water-saving measures where necessary. This can lead to both cost savings and a reduced environmental impact, aligning with sustainability goals in the hospitality industry. Benchmarking modifiers for water use. This table presents benchmarking modifiers for water usage in different areas of a hotel, categorized by climate, temperate, Mediterranean, and tropical. It compares the water consumption for overnight guests, laundry, covers, pool, employees, no cooling tower, and gardens, with the base water consumption for a 150 square meter area. The modifiers are calculated based on the actual area and are expressed in cubic meters per guest, allowing for an estimation of water consumption tailored to specific hotel characteristics and environmental conditions. Topic to be covered. In this section, we will cover several important topics regarding water management in hospitality. We will explore guidelines for guest washrooms, innovative water-saving technologies, the workflow of laundries, eco-friendly pools, swimming pool water treatment methods, sustainable spa practices, and best practices for gardens. Additionally, we will address water quality, including standards, common problems, and solutions, as well as prohibited chemicals in water treatment. Guidelines for guest washrooms. To enhance guest comfort while conserving water, consider investing in high-quality towels. Adding plants can introduce a natural touch to the washroom. Decorative baskets and additional storage options can enhance organization. Including a bathroom rug and wall decor can elevate the aesthetic. Don't forget to offer robes, slippers, and essential shower amenities to ensure a luxurious experience. Water-saving technologies. Several water-saving technologies can significantly reduce consumption. A pressure-reducing valve helps lower water pressure to save water. Faucet aerators mix air with the water flow, reducing usage. Water-efficient urinals and sinks are specifically designed to minimize consumption. A vacuum flow valve can conserve water in commercial plumbing, while a cistern volume adjusting device optimizes flush volume. Finally, dual flush toilets provide options for different water needs per flush. Workflow of laundries. The laundry workflow begins with collecting and sorting dirty linens at the source. Safely transporting these linens to the laundry area is crucial. During washing, it's important to use the correct temperature and detergent mix based on the type of textile. Quick drying and ironing processes are essential to prevent contamination. Finally, clean linens must be delivered back to their respective wards promptly. Eco-friendly pools. To maintain eco-friendly pools, consider using fewer chemicals and utilizing a pool cover to reduce evaporation. Opting for a cartridge filter instead of a sand filter can enhance efficiency. Installing a pool pump timer, solar pool heater, and using dual speed or variable speed pumps will help save energy. Keeping the pool filled year-round reduces maintenance needs and promotes efficiency. Swimming pool water treatment methods. Swimming pool water treatment can be managed through various methods. Chlorine and chlorinated isocyanurids are common, but salt chlorination offers a safer alternative. Ionization uses minerals to purify water, while ozone generation effectively kills bacteria. Bromine-based disinfectants and UV disinfection reduce chemical use, and natural pools or swimming ponds provide a chemical-free option for water treatment. Spa. Sustainable spa practices are essential for eco-conscious operations. Implement eco-friendly lighting and energy-efficient HVAC systems to reduce energy consumption. Use low-flow faucets to conserve water and minimize laundry loads and waste. Conducting energy audits can identify further efficiency opportunities, and choosing skin-friendly products will enhance the guest experience while being environmentally responsible. Garden. Incorporating eco-friendly practices in gardens includes recycling and reusing materials. Choosing local, eco-friendly materials and permeable paving can minimize environmental impact. Water conservation techniques, investing in green roofs, and enhancing soil quality with compost are effective strategies to create a sustainable garden environment. Water quality. Water quality encompasses chemical, physical, and biological characteristics that are vital for uses such as drinking and swimming. Adhering to water quality standards ensures regulatory compliance. Water quality standards. The table shows water quality standards for various designated best uses. Class A water is suitable for drinking water source without conventional treatment but after disinfection, with a maximum of 50 total coliforms organism mpn per 100 ml, pH between 6.5 and 8.5, dissolved oxygen 6 mg per liter or more and biochemical oxygen demand of 2 mg per liter or less in 5 days at 20 degrees Celsius. Class B water is suitable for outdoor bathing, organized, with a maximum of 500 total coliforms organism mpn per 100 ml, pH between 6.5 and 8.5, dissolved oxygen 5 mg per liter or more and biochemical oxygen demand of 3 mg per liter or less in 5 days at 20 degrees Celsius. Class C water is suitable for drinking water source after conventional treatment and disinfection, with a maximum of 5,000 total coliforms organism mpn per 100 ml, pH between 6 to 9, dissolved oxygen 4 mg per liter or more and biochemical oxygen demand of 3 mg or less in 5 days at 20 degrees Celsius. Class D water is suitable for propagation of wildlife and fisheries, with pH between 6.5 to 8.5, dissolved oxygen 4 mg per liter or more and free ammonia, as N, of 1.2 mg per liter or less. Class E water is suitable for irrigation, industrial cooling, controlled waste disposal, with pH between 6.0 to 8.5, electrical conductivity of 2250 micromos per centimeter at 25 degrees Celsius, sodium absorption ratio of 26 and boron of 2 mg per liter. Water quality below Class E does not meet the criteria for any of the designated best uses. Water quality problems and solutions. Common water quality problems include suspended solids, which can be treated through sand filtration. High salt content can be addressed with desalination techniques like ionic or reverse osmosis. For iron contamination, potassium permanganate treatment combined with filtration is effective. Acidity can be managed by removing carbon dioxide and dosing alkaline liquids, while corrosivity can be mitigated with specific chemicals. Finally, addressing hardness requires evaluating the Langelier saturation index and the Reisner stability index for appropriate treatment. Prohibited chemicals in water treatment. Certain chemicals are prohibited in water treatment due to their adverse effects. Chromates are often banned in cooling towers, while hydrazines are restricted in boilers. Amines are also prohibited when steam comes into contact with food, ensuring that water treatment processes remain safe and effective. Topics to be covered. In this section, we will discuss various aspects of wastewater treatment. We will cover the wastewater treatment process, how to install a water treatment plant, indicative values for sewage discharge, guideline values for treated water, methods of wastewater treatment including preliminary, primary, secondary, and tertiary treatments, and the reuse of treated water. Wastewater treatment. Wastewater treatment is the process of converting wastewater into water that can be safely returned to the environment. This process typically takes place in specialized facilities known as wastewater or sewage treatment plants, where different methods are employed to purify the water. Wastewater treatment process. The wastewater treatment process consists of several key steps. First, bar screening removes large debris. Next, grit removal separates grit from the wastewater. The primary clarifier allows solids to settle, followed by aeration, which adds oxygen for biological treatment. The secondary clarifier further settles solids before chlorination disinfects the water by killing bacteria and viruses. Water analysis and testing are then conducted to ensure the treated water meets quality standards before effluent disposal returns it safely to the environment. How to install a water treatment plant. Installing a water treatment plant begins with inspecting and placing the tank in the desired location. Next, excavate the hole while considering drainage slopes to ensure proper flow. It's essential to use the correct backfill and install inlet and outlet pipes accurately. Electrical wiring must be connected, and the tank covered securely. Finally, ensure proper ventilation arrangements are in place to facilitate effective operation. Here are the indicative values for treated sewage discharge, measured by various pollutants. The pH should range between 6 and 9. Biochemical oxygen demand, or BOD, should be 30 mg per liter or less. The chemical oxygen demand should not exceed 125 mg per liter. Total nitrogen and phosphorus levels should be kept below 10 mg per liter and 2 mg per liter, respectively. Oil and grease levels should be limited to 10 mg per liter, while total suspended solids must remain at 50 mg per liter. Total coliform bacteria should be at 400 mpn per 100 ml or less, with a temperature increase of less than 3 degrees Celsius. Finally, total residual chlorine should be under 0.2 mg per liter. The guideline values of treated wastewater for irrigation are crucial for ensuring safe use. For coliforms, the geometric mean should be less than 200 per 100 milliliter. For intestinal nematodes, the arithmetic mean number of eggs should be limited to just 1 per liter to ensure safety for agricultural applications. Method of wastewater treatment methods. Wastewater treatment methods can be categorized into 4 main types: preliminary treatment, primary treatment, secondary treatment, and tertiary treatment. Each stage plays a critical role in effectively purifying wastewater before it is released or reused. Preliminary treatment. Preliminary treatment involves screening out debris to protect equipment. Common methods include bar screens, grinders, and grit chambers. This stage effectively removes large particles, sludge, and suspended solids, resulting in a 25 to 40% reduction in biochemical oxygen demand, a 40 to 60% reduction in suspended solids, and a 45 to 55% decrease in coliform levels. Primary treatment. Primary treatment focuses on allowing solids to settle in settling tanks, which facilitates further separation. This stage removes larger suspended solids from wastewater and can achieve a reduction in biochemical oxygen demand of up to 30 to 35%, contributing significantly to overall water quality improvement. Secondary treatment. Secondary treatment utilizes biological processes to reduce organic material in wastewater. Oxygen is critical during this phase to support bacterial activity. Common methods include fixed film systems, suspended film systems, and lagoon systems. This treatment can result in an impressive 85 to 95% reduction in biochemical oxygen demand and suspended solids, with 90 to 99% of coliform bacteria removed, making it a vital step in the treatment process. Tertiary treatment. Tertiary treatment is the final stage of wastewater treatment, aimed at removing any remaining disease-causing organisms. Methods used during this stage include sand filtration, microstraining, chemical precipitation, and UV treatment. The outcome is high-quality treated effluent that is suitable for reuse in various applications. Reuse. After undergoing tertiary treatment, treated water can be repurposed effectively. It can be utilized for irrigating hotel grounds, returning to gray water recycling systems, and other applications that benefit from treated water, thus promoting sustainability and resource conservation. Thank you for your attention. For more details, please contact TSD Office, Engineering GHG. We appreciate your interest in ESG initiatives.